Welcome back to another explainer where we take complex ideas and make them crystal clear. Today, we're diving into the invisible puppet strings that control, well, literally everything in our physical universe. Let's kick things off with an everyday mystery. Have you ever noticed how you have to fight so incredibly hard on a bike when you're riding into a headwind? Or, on the flip side, why you don't just float right off your bicycle seat and up into the sky? That intense, literal uphill battle against nature is actually the perfect example of what we're talking about today. A cyclist pushing hard against the pedals is actively battling unseen pushes and pulls that shape every single movement we make. We call these invisible strings forces, and they are happening all around you right at this very second. So here is our roadmap for today's explainer: the invisible forces, exploring types of forces, the pull of gravity, mass versus weight, and finally, the power of air resistance. Section 1. The invisible forces. So what actually is a force? Well, at its most basic level, it's simply a push or a pull that has the power to change how an object behaves. A force can make a totally stationary object suddenly move. It can forcefully stop an object that's already in motion. It can even change an object's direction or entirely alter its physical shape. It is the ultimate instigator of change in the world of physics. Now, even though they're invisible, we can actually measure these pushes and pulls in the real world. We use a device called a force meter. It relies on a stretching spring inside a casing. So when a force is applied to the hook at the end, the spring stretches out and a pointer moves along a scale to give us a super precise reading. We measure that reading in a unit called newtons, represented by a capital N. Section 2. Exploring types of forces. Forces neatly divide into two broad categories. First up, we've got contact forces, which, as you might guess, require physical touch. This includes applied force, like when you physically shove a heavy box; normal force, which is the floor pushing back up against that box; frictional force, which opposes and slows down that motion; and spring or tension forces that happen through a pulled rope or wire. On the flip side, we have distance forces. These are fascinating because they act without any physical touch at all. We're talking gravitational force, electrical force between charged objects, and magnetic force. And here's the kicker: forces almost never act alone. Take a windsurfer, for example. She is actively harnessing thrust from the wind to move forward, while utilizing lift to stay right above the surface of the water. But simultaneously, she's fighting off drag, which constantly resists her forward motion, all while dealing with the constant downward pull of gravity. It is a spectacular, dynamic balancing act of directional forces. Section 3. The pull of gravity. Let's talk about the big one: gravity. Gravity is the universal force of attraction. This basically means any two objects in the universe that have mass will inevitably pull on each other. Earth's gravity is what pulls a dropped apple straight down from a tree. And on a much grander scale, this invisible attractive force is exactly why planets orbit the sun, and why the moon stays securely locked in orbit right around our Earth. The really crucial point to remember here is the direct relationship between mass and gravitational pull. Bigger mass simply means bigger gravity. To put this into perspective, think about the planets in our solar system. Jupiter has an absolutely massive diameter of almost 143,000 kilometers compared to Earth's roughly 12,700 kilometers. Because it has so much more matter, Jupiter easily commands the strongest gravitational pull out of all the planets. But here's a totally mind-bending fact for you: gravity isn't even identical everywhere right here on Earth. As our source material points out with the example of climbing Mount Kinabalu, if you hike way up to a towering mountain peak, the gravitational force pulling down on you actually gets slightly weaker. Why? Simply because you are moving further away from the dense center of the Earth compared to when you're standing way down in the valley below. Section 4. Mass versus weight. This brings us to a huge point of confusion: mass and weight. People mix these two up all the time, but they are absolutely not the same thing. Mass is simply the amount of matter or stuff that an object is made of. Your mass stays exactly the same no matter where you travel in the universe. Weight, however, is a measurement of the effective gravitational force pulling down on that mass. Because gravity changes depending on where you are, your weight changes right along with it. Let's look at a concrete example. Think about a 10-kilogram mass. On Earth, our gravity pulls hard, so it weighs 98 newtons. But if we take that exact same 10-kilogram mass to the moon, where the gravity is much weaker, it only weighs 16 newtons. And what if we take it into deep outer space? Well, the mass is still exactly 10 kilograms, nothing vanished, but with zero gravity pulling on it, its weight plummets to absolute zero.
Section 5. The power of air resistance.
Now, whenever an object moves through the air actually fights back. It experiences a frictional contact force called drag, which vigorously opposes motion. A parachute, for instance, is purposefully designed to create a massive surface area just to maximize this upward drag. It generates enough air resistance to safely counteract the severe downward pull of gravity, slowing a skydiver down to a safe, survivable landing speed. We actually see this exact same concept applied in professional sports too, just in reverse. An Olympic swimmer maintains a lean physique strictly to reduce their surface area. By making themselves as sleek as humanly possible, they minimize the drag or resistance from the water. Less resistance means they can swim much, much faster. It's all about intentionally manipulating these forces to your advantage. All right, let's do a quick mental experiment together. I want you to imagine dropping two objects from the exact same height at the exact same time. In one hand, we have a fuzzy, solid tennis ball. In the other, a delicate, extremely lightweight feather. In a normal room, we instinctively know the ball hits the ground first, right? The feather catches the air and floats down slowly because of high air resistance. But what happens if we put both of these objects into a sealed chamber and suck absolutely all the air out to create a pure vacuum? With no air at all, which object hits the ground first then? The answer is honestly mind-blowing. In a true vacuum, there's absolutely zero air resistance to push back and oppose motion. Without that upward push of drag slowing the feather down, Earth's downward gravitational pull is literally the only force acting on the objects. And because gravity accelerates all objects equally, regardless of their mass or their shape, amazingly, the feather and the heavy tennis ball will crash into the ground at the exact same millisecond. So let's tie this all together. It's incredible to realize that every single movement we make, every single moment of our daily lives, is a delicate balancing act of these invisible strings. From the friction keeping our shoes from slipping on the sidewalk, to the gravity holding our entire solar system together, forces absolutely dictate reality. Which leaves us with a fascinating and maybe slightly terrifying question to ponder. What would happen to reality as we know it if just one of these fundamental forces simply stopped working? Thank you so much for joining me for this explainer. And be sure to keep looking for the invisible forces in your own world.